All right, physics reaction video number 92. Uh, Today, university physics, so college level, we guess. Looks like it's prep for lab. Not sure if it's a virtual lab, a real lab, or what, so let's get going.
Okay, we're going to be discussing Laboratory 3 from Physics Laboratory Manual by David H. Lloyd, fourth edition. Um, Laboratory 3 discusses using the vector table where you place a particular mass at one angle and then you place another mass at another angle, and then you experimentally find the resultant. The resultant would be here, but what you do is you find the equilibrant that balances out all of these forces that you're.
Cool. So just a couple of things about the setup. Loved using, real life things. So it looked like an Apple Pencil and a pen, and I'm excited that it's an Apple Pencil. Maybe we'll see some Apple Pencil drawings. Maybe that wasn't an Apple Pencil. I don't know. And just it was amazing how quickly he sort of got to the point of what the vector table does. Again, I'm not sure if this is a lab that they're supposed to do on their own or a lab they're coming in to do and they watch this video first. Still not clear.
Putting together, and I have a video of that. I'll put a link to that video
Cool.
of doing it experimentally. But we're going to be talking about doing the graphical method and the analytical method. And we're going to, in addition to the analytical by hand, I'm going to show how to do it using Excel.
Cool.
So it might be of interest to others, not just to my physics class. So let's share the screen, and here it is. So I'm going to dismiss the my image. There's no reason for you to see me.
I just want to comment on the point he just made. So when you add your video to a video, like I'm doing right now, it does a number of things. First of all, it can really provide, of course, facial expressions and things like that. It makes the size of the video file, 10 times larger, because it's where all things are moving, whereas usually you're staring at a static image for a long time. And of course, it covers up a little bit of space. I think the reason that he shut it off was that it was covering up space. But it is interesting to think about the facial expressions and other sort of nonverbal communication that you can add with your video. I'd love to hear in the comments what you guys think about that. Obviously, I did make the decision to put my own pictures in these videos that I'm doing. But of course, I wouldn't have to.
I want you to see the screen. So we're doing vector addition example, the graphical method. Now, in the experimental method, I had 200 grams, 0.2 kilograms at 30 degrees and 0.2 kilograms at 120 degrees. So experimentally, we found the equilibrant to be 285 grams at 257 degrees, which that translates to a resultant. If we multiply 0.285 kilograms by 9.8, we get 2.79 newtons at 180 from 257, gives 77 degrees. Now we're going to do that. So those are our results. We're going to do it graphically. So we have 1.96 newtons. I just picked an arbitrary scale. I tried to make it big enough so that, if you make it real small, you'll end up with real inaccurate results.
Just a quick comment on that. I love how he's talking about what has to be sort of accurate and what sort of arbitrary choices you have to make. So he talks here about the arbitrary scale. Of course, he means the distance scale. What can't be arbitrary is the angles. And so, of course, I think that it's really important to help students understand that there is some arbitrariness to this. But then there's other things that are going to track independent of those choices. And of course, if a student were to choose a different scale horizontally than vertically, then it screws all the angles up. So, of course, any choice you make about horizontal, boom, you're now locked into vertical. But as soon as you do that, that first arbitrary choice, everything's going to work out. And I think that's really cool how he's commenting on that.
So 1.96 newtons at 30 and 1.96 newtons at 120. We can translate this one over to here and use a head to tail method to get the resultant. And if we draw the resultant, I measured it to be 2.74 newtons. Well, the 2.74 newtons divided by 9.8 meters per second squared gives 0.28 kilograms, or 280 grams. So experimentally, I got 285 grams at 77 degrees. Graphically, I got 280 grams at 75 degrees. And so that's how you do the graphical method. Now we're going to do the analytical method. I have my 200 grams, which is 1.96 newtons in this direction, and then 1.96 newtons in this direction at 120. And
just a really quick comment. Math professor taught me a really great skill. If you're going to draw a circle with a center, draw the circle first, then the center. He's actually done a great job here. I wanted to comment on a couple of the things here that I'm noticing. Because the magnitude of the two forces is the same, the real difficulty of this problem is that it's cocked up at 30 degrees, right? So if it were just sort of horizontal and vertical, and you have, oh, wait a second, then you have, an equilateral triangle, and it's not equilateral. What's the word I'm looking for? Isosceles triangle. A right isosceles triangle. There's all kinds of things that we can learn about that, because in fact the length of this is going to be the same length as the hypotenuse of this triangle. And so it seems to me that the 75 degrees because the two amounts are the same, would have been straightforward. And so, but it's really, really interesting how he's just sort of cramming it through as though, we don't need to use that happenstance, that lucky happenstance. And I love it, right? Because then any other measurements that they make would have yielded, this approach is going to work the same.
And we want to analytically find the resultant. So, to get the x value of F1, it's 1.96 times cosine of 30 degrees is 1.697 newtons. F1y is using the sine. You get 0.98 newtons. F2, I got minus 0.98 newtons for the x. You can see it's a small vector over here. And for the y, it's 1.697 newtons. Now, to get the resultant, you have to add the components. So the Rx components, F1x plus F2x, is 1.697 newtons plus a minus 0.98 newtons, and you get a 0.717. Notice it's in the positive direction, and indeed, you can see a 0.717 is a little vector in this direction. That's the x component. The y component is 2.
Just a real quick praise here. I really thought it was great how he focused on this negative sign and then the fact that this is a positive sign. So sometimes all we do is we comment on the negative signs and put a lot of energy and attention into that. But he's actually paying attention to something that's not even written down here, this non-written positive sign here. He went up to the drawing and he talked about, oh yeah, that is to the right. I love that, because of course all we mean by negative signs in these kinds of approaches is just it's a directional signifier. It's not, about its morality or something. The other thing that I find really interesting is just I wonder how the students react to having to multiply every single thing by 9.8, right? Because we would have gotten this answer down here, this 75, the same if we hadn't bothered to put all the 9.8s in, right? Now this answer would have been different. You have to put it in for this number to be right. So I do wonder sometimes how much the students get frustrated about that, having to just multiply all their numbers by 9.8. But I love how he's just being super consistent with it, just rolling along with it, and doing a great job, especially with these signs.
2.677, that's up here along the y-axis. So we just we summed the components to come up with Rx and Ry. Now to get the magnitude, you take the square root of the sum of the squares of the components. So 0.717 newtons squared plus 2 0.677 newtons squared. Take the square root of that, you get 2.772 newtons. And to get the angle, it's the inverse tangent of Ry over Rx, or the inverse tangent of 2.677 newtons divided by 0.717 newtons, and you get 75 degrees.
A quick point here that I really like what he did here. He was very careful to make sure to put the units in here, because that's what we're talking about. But of course, all of the trigonometric functions need their arguments to be unit free. And so you can see it. Aha, the units cancel. So I really like how he stuck it in, but it's very clear that it's in both places.
Now, what is that? I've got 2.772 newtons. What is that in grams? It's 2.772 newtons divided by 9.8 meters per second squared. That gives me 0.283 kilograms, or 283 grams. And we can see I got 283 grams. Analytically, I got 280 grams graphically, and I got 285 grams experimentally. So you can see there's a bit of error, and that's part of what this this exercise was supposed to show you. The analytical method is by far the most accurate. The graphical and the experimental, they're not as accurate, but they get you in the ballpark. Certainly 285 and 280 is very close to 283 grams. Now, let's do the same thing using Excel. I have F1, F2.
I just want to pause for a second. I'm curious about this Excel approach, but you know, it's really interesting to think about which is most accurate, because I think the students are going to say, no, I literally in the lab, it was 200 and whatever it was, whatever the experimental value was. That's how much was on there. I weighed it. That is for sure what it is. So to say that the analytical method is more accurate, or that the graphical method might have some other issues going on, all of this comes down to measuring the angle, right? Because you can get the mass really, really accurately, although I suppose there's some, you have to decide whether you're weighing the mass of the strings or the ropes, depending on how you do this. But in the mass, you can get super, super, super accurately, but it's usually the angles that have problems. And of course, we're using the angles in all three. Well, yeah, the measurement in the experiment is measuring an angle. Say, I found it to be at this angle. The graphical method is trying to replicate angles measured in the lab and drawn again on a sheet of paper. And the analytical method is using those angles in the trigonometric calculations. And so it's really interesting to think about where any sort of error and error propagation is happening in this problem. All right, let's check out this Excel.
This is the mass, this is the angle, this is the force, just the 9.8 times this, 9.8 times this gives you the force. Now let's break it into its components. Now let's look at A to calculate. I'm just going to do the x component. To calculate the x component, you can see the equation at A. You take the force cell, which is D3.
All right, very, very cool. I've just noticed in the time I'm probably going to bring this to a close, but here's something I love about this. So when students or we present Excel or spreadsheet information, what actually matters is this information, like how it came to be. So I really love this way of presenting it. Just putting little labels here and then telling people what it is. Now, when my students turn in spreadsheets, sometimes I will just click in the cell to see this stuff, and they know that I'm going to do that. But I just love how well presented this is. And I love, again, yet another way to help students understand what's going on with this problem. Man, this was really great. All right, everybody, I hope you have a great day. And remember, physics teachers are awesome.